In this video on derivatives, we will be dealing with the geometrical meaning of derivative, and we will find the derivatives of some basic functions like polynomial functions, quadratic functions, logarithmic and exponential functions. Before going into derivatives, we'll just refresh ourselves about the concept of slopes. If I have a line with y and x in this way, then slope of the line is y over x. And if this is the angle that the line makes with the x-axis, if theta is the angle, then tan theta will be equal to y over x. It is obvious from the right angle triangle formed by the line with the x-axis. So what is slope of the line? Slope of the line is nothing but tan theta, where theta is the angle of that the line makes with the x-axis. Let's consider a function and 2 points on it, p and q. As q moves towards p, the chord pq becomes a tangent at p. So the chord slowly moves down and it becomes a tangent at p. Even though the p and q looks far away here, q is supposed to be very close, very close to p. The function has been zoomed in order for us to see it clearly. Let's consider the same diagram. Q and P are there, and Q is very close to P, say delta x away from x of P and delta y away from y of P. Therefore, tan theta here becomes dy over delta y over delta x, where theta is the angle shown here. As q moves towards p, that is, as q tends to p, the chord tends to move and become the tangent at p. At the same time, the value of delta y tends to become 0, and also that of delta x. So there are two more limiting conditions, delta y tending to 0 and delta x tending to 0. Also, the theta, which was the angle of the chord with the x-axis, now changes and becomes, say, phi. So the another limiting condition here is the theta changes to phi. We have all these four limiting conditions happening at the same time. So in order to make a limiting equation, in order to apply the limits on both sides of this function, in order to apply the limits on this equation, this side of the equation has theta, therefore we will apply this limit on this side, that is limit theta tending to phi of tan theta, because theta is the variable on this side. And on this side x is the variable, and we can apply this limit for the right hand side. So limit delta x tending to 0 of delta y delta x becomes the limit of the right hand side, and limit of theta tending to phi of tan theta becomes the limit of the left hand side. As theta becomes phi, tan theta becomes tan phi. This whole limit is going to be rewritten as dy dx. Just it is a notation. Dy dx is nothing but limit delta x tending to 0 of delta y over delta x, that is the small change in y over small change in x, as the change in x tends to 0. This is just a notation. So what exactly is dy dx? Dy dx is nothing but the slope of the tangent at a particular point on the curve. This is also called the derivative of a given function. Let's see how to actually find this dy over dx. Consider the 2 points again. Remember, they are very close, but they are zoomed here. Let's say this point is x comma y, and let me give an increment of a small value h to the x coordinate of the first point, so that the x coordinate of the second point becomes x plus h, and what happens to the y we'll see it soon. We have the function y as f of x, that is f of the x coordinate. Therefore, this point becomes f of x and this y becomes f of x plus h. What will be the slope of the chord? Slope of a line is change in y over change in x. So slope of this purple line will be change in y, which is f of x minus f of x plus h minus f of x, and the x values are x plus h and minus x. The x cancels and you get only h in the denominator. When does this chord become a tangent? The chord becomes a tangent when the q approaches p or when the h approaches 0. So on the limiting condition as h approaching 0, the slope of the chord becomes the slope of the tangent. We just saw that slope of the tangent is equal to tan theta. Therefore, slope of the tangent is nothing but f of x plus h minus f of x over h as limit h tending to 0, and we also saw that slope of the tangent is dy over dx. Therefore, the derivative dy dx is computed as, therefore dy dx is found out using this formula, and this formula is known as the first principle method. Using this formula, we can find the derivative of any function. We'll be seeing that soon. Derivative of a function y equal to f of x can be written in different notations. The first notation which we have so far seen is dy over dx, that is the derivative of y with respect to x. We can also write it as y dash, and there are some other notations, f dash or f dash of x, or we can also write it as d over dx of f of x. So we can just put this function inside and say d over dx of this is so and so. So these are some of the notations used to represent the derivative of a function y equal to f of x with respect to x. Let's see how we can find the derivative of x to the power of n. Let's say f of x is equal to x power n, and we know that the first principle method states this f dash of x, which was dy dx, is equal to limit of f of x plus h minus f of x over h as h tending to 0. So we need f of x plus h, we need f of x. We are given f of x is equal to x power n. Therefore, f of x plus h is equal to x plus h power n. Just substitute these two values in this place. So x plus h whole power n for f of x plus h minus x power n for f of x over h as limit h tending to 0. How to compute this? Let's rewrite this h as x plus h minus x as before. This is how we got this s. If I substitute x plus h as y, then I get y power n minus x power n over y minus x. So that is what we get if I substitute x plus h as y. But what happens to the limits? H tending to 0 has become y tending to x. Why? As h becomes 0, it is obvious that y is equal to x. Therefore, as h approaches 0, y becomes x. Therefore, the limit changes from h approaching 0 to y approaching x. Because we don't have any h here, I cannot use h tending to 0 in this limit. Now, how does this look like? This looks like the equation limit x tending to a of x power n minus a power n over x minus a, which we have done in the video on limits. The answer for this is n a power n minus 1. This is similar to this limit, only that there is a difference of y is in the place of x and x is in the place of a, and the limiting condition is y tending to x, which is x tending to a here. Therefore, this is the answer, and we just have to substitute the a as x here. Therefore, the answer will be n x power n minus 1. Therefore, the derivative of x to the power of n is equal to n x to the power of n minus 1. This is a very important result which needs to be kept in mind. So how exactly will you use this? Let's say we have the function x power 3. By the formula n x power n minus 1, then it is 3x power 3 minus 1. Therefore, the derivative answer will be 3x square. If it was x power 10, then it is obviously 10 n x power 10 minus 1, which is 9. Therefore, x power 10, derivative of x power 10 is 10x power 9. What about x? X can be rewritten as x power 1. Therefore, using the formula 1 x power 1 minus 1, which is 0. Therefore, it is 1. X power 0 is 1. What about a constant k, for example 5 or 8 or 10 or negative 5 or whatever? We can write this k as k times x power 0 because this is 1. Using the formula again, x power 0 can be rewritten as 0 x power 0 minus 1, which is negative 1 here. Therefore, we get k times 0 times x power negative 1, which is 0. Therefore, derivative of a constant is 0 and derivative of x is 1. These are again important results to be noted, which we will use it very often. What about 1 over x? 1 over x can be taken as x to the power of negative 1. Using the formula again, negative 1 x power negative 1 minus 1 n minus 1, which is negative 1 minus 1, which is negative 2. I can write this as x to the power of 2 in the denominator. Usually the answers are given with positive index. 1 over x square can be taken as x to the power of negative 2. Negative 2 minus 1 is negative 3. Therefore, this is negative 2 over x cube. So far, we have seen positive powers, 0 and negative powers. And these are the results of such functions with positive, negative and 0 powers. What about the fractional powers? We can use the same formula for the fractional powers. So, x power 1 over 3 becomes 1 over 3 x power 1 over 3 minus 1, which is, this is negative 2 over 3. Therefore, this is 1 over 3 x to the power of 2 over 3. Again, I said it is always advisable to give the answer in positive powers. Here, x power half is nothing but square root of x. So, if it is square root of x, take it as x power half and apply the formula. Half x power half minus 1. Half minus 1 is negative half, which is 1 over root 2. Therefore, it is 1 over 2 root x. So, half, which is 1 over 2, this one, x power negative half is 1 over root x. X power negative half is 1 over root x. So, what happens for 1 over root x? Apply the formula again. If you have a problem with 1 over root x, take it as x to the power of negative half and use the formula. Negative half, x power negative half minus 1, which is, this is x to the power of negative 3 over 2. Therefore, it is negative 1 over 2 x power 3 over 2. I can also write it as negative 1 over 2 root of x cube. If you are very good in exponents, you can just rewrite this as root of x cube. This is how we use the formula for finding the derivative of any function in the form x to the power of n. If I have a constant before the x power n, the constant is retained as it is, and this x power n is changed to n x power n minus 1. For example, if I have 5 x power 3, then my answer will be 5 is retained as it is. It will be 3 x power 2. Therefore, the final answer will be 15 x to the power of 2. Let's see how exactly a polynomial is differentiated. The word differentiated means how to find the derivative of a function. To find a derivative of a function, is differentiation. So let me give you an example of a polynomial function. Say for example 3x to the power of 5 minus 4x square plus 1 over x minus 2 minus 1 over x to the power of 5. How do we do this? We just have to find the derivative of each function and put the signs in between. So 3x power 5 is nothing but 3, keep it as it is, 5 to the times x to the power of 4, 5 n x power n minus 1. 4x square becomes 4, keep it as it is, 2 x to the power of 1. 1 over x just now we did, which has to be taken as x to the power of negative 1. Therefore this became negative 1 over x square. We just saw this function. 2 is a constant, therefore it becomes 0. A constant, a derivative of a constant is 0. 1 over x to the power of 5 should be taken as x to the power of negative 5. So this is negative 5 x to the power of negative 5 minus 1, which is negative 5 x power negative 6. Therefore this is negative 5 x power negative 6. Just introduce the signs as given in the question. Here it is minus. Here again it is minus. So final answer will be 15 x to the power of 4 minus 8x, plus minus is minus 1 over x square, and there is no value here, and minus minus is plus 5 over x power 6. X power negative 6 should be written as 1 over x power 6. So this is the derivative if I have this as f of x and this is f dash of x. Derivative of, this is the derivative of the given polynomial function. It's not difficult to find the derivative of polynomial function. Let me give you one more example. Say I have 3 root x minus 2 over root x plus 5 x to the power of, say for example 10. So root x is x power half, which became half x power negative half. You should remember this. 1 over root x is x power negative half, which became negative half x power negative 3 over 2. So we have to just find out the values of each of the function on finding the derivative. So 3 is kept as it is. Root x becomes half x power negative half. 2 is kept as it is. 1 over root x is negative 1 over 2 x power negative 3 over 2, and this is obviously 50 x power 9. By now this should be easy for you. And introducing the signs in between, here it is a minus sign and here it is a plus sign. So simplifying this, 3 over 2 root x, x power negative half is 1 over root x, and minus minus is plus, 2 cancels, therefore 1 over x to the power of 3 over 2 or root of x cube, either way is right, plus 50 x to the power of 9. This is the derivative of the given polynomial. Let's continue finding the derivative of trigonometric functions. If I have f of x is equal to sin x, then I need to have f of x plus h in order to substitute it in the first principal formula. So this is sin of x plus h. The first principle says limit h tending to 0 of f of x plus h minus f of x over h, which is limit h tending to 0 sin of x plus h minus sin x over h. Let's use the formula for sin a plus b here. So it is limit h tending to 0 sin a cos b plus cos a sin b and minus the sin x which is there. over h. Now I can combine these two and write it as sin x common times cos h minus 1, and this is written separately over h. Now I am going to split it into two terms and write the limits separately. Limit h tending to 0 of sin x of cos h minus 1 over h plus limit h tending to 0 of cos x sin h over h. Since sin x doesn't involve h, it can be taken out, sin x, and the limit is applied only for this part, cos h minus 1 over h. Same comes here, cos x can be taken out and the limit is applied only for sin h over h, which we know obviously is 1. We have done this in the video on limits. Therefore, this part is cos x times 1. And what about this part? We'll do it now. So we need to find the limit of cos h minus 1 over h as h tending to 0. If I substitute 0 here, it becomes 0 over 0, which is not acceptable. So let's just cook up cos h minus 1. For this we need to use the formula cos 2h is 1 minus 2 sine square h. So cos 2h minus 1 is minus 2 sine square h. If it is h instead of 2h, then we'll have, in the place of h, we'll have h half of h. This is 2h becomes h, therefore h becomes half of h. I'm going to substitute this in this place. So this becomes limit h tending to 0 of minus 2 sine square h over 2 divided by h. Minus 2, I'm just writing this into 2 sines, sin h over 2 times sin h over 2 over h, and this 2 I can write it as over h over 2. 2 over h is denominator, in the denominator will be h over 2. I can write it like sin h over 2 over h over 2 times sin h over 2. If I will apply the limit now, this limit becomes 1 and this becomes 0. Therefore, finally the answer for this limit is 0. Therefore, here we have 0 plus cos x, which is cos x. Therefore, the derivative of sin x is cos x. Again, very, very important result to remember. Let's move on to cos. We'll do it in the same way. Let's start with f of x is equal to cos x, and f of x plus h is equal to cos x plus h, and we'll apply it in the first principle method. I'm going to write it directly without writing the formula. Cos x plus h minus cos x over h. We use the expansion of cos x plus h now, which is cos a cos b minus sin a sin b minus the cos x which is present there, whole divided by h. Again, let me combine the terms with the common functions. Cos x is common, so let me combine these two terms with cos x minus, this is separate, so sin x sin h over h. So this and this are combined to form here, and this is here. Now we just saw that cos h minus 1 over h was equal to 0, therefore this becomes 0, and this is sin x comes out, and it is limit of sin h over h, which is 1, so times 1. Therefore, the answer will be negative sin x. So it is very easy now to find the derivative of any function using the first principle. We just now found that derivative of cos x is negative sin x, which has to be remembered again. Let's proceed to find the derivative of the exponential function. Exponential function is of the form e power x. So instead of y, let me write it as f of x is equal to e power x, so that we'll know what is f of x plus h, which is e to the power of x plus h. Substituting in the formula for first principle, limit h tending to 0 of e power x plus h minus e power x divided by h. F of x plus h minus f of x over h as the limit h tending to 0 is your derivative. Again, collecting the common terms, e power x plus h is e power x times e power h. So this is e power x times e power h minus e power x over h. Let me collect the common e power x from both the terms. Then the first term remains with e power h and the second has 1 in it, and this is the simplification of this to this. Again, I cannot substitute h is equal to 0 here because 1 minus 1 over 0, which is 0 over 0 form, so it is not possible. I can take the e power x out anyway and see what happens to this limit e power h minus 1 over h. This function is of the form e power x minus 1 over x. Let's see what happens to this function x as x approaches 0. This is the function e power x minus x. Let's see, as the point moves closer to the x value as equal to 0, you can see that the value of y approaches 1. At the value 0, x is equal to 0, there is no value of the function, and again it starts coming out once it crosses the y-axis, that is once the x value crosses the 0. So as x approaches 0, the value of y comes to 1. Though you don't have the value at x is equal to 0, the limiting condition is 1. As x approaches 0, the function approaches 1. Therefore, the limit as x tending to 0 of e power x minus 1 over x is equal to 1. Hence, this limit becomes 1 and we are left out with only e power x. So the conclusion is the derivative of e power x remains as e power x itself. There is no change in the function. Let's move on to logarithmic function. By logarithmic function, I mean the logarithm to the base of e. That is, log x to the base of e is usually written as ln of x. Therefore, f of x plus h will be ln of x plus h. This is a natural logarithm. So f dash of x is equal to limit h tending to 0 of ln of x plus h minus ln of x over h. Using the property of logarithms, this becomes x plus h over x over h. Ln of a minus ln of b is ln of a over b. Again, we cannot substitute the value of h as 0 directly here. It gives you 0 over 0. Hence, again, we need to cook up a little bit. I can write this as 1 over h ln of x plus h over x. Again, I will rewrite it as 1 over. I am just simplifying this. I am dividing the two terms by x and I get this. Here I am just going to make this part as x over h so that it goes with h over x. So if I make this as h over x ln of 1 plus h over x, then I have to multiply this by 1 over x because they cancel and give you the same expression. So I'm just rewriting. This is the part which is tricky here in this question. You have to introduce the x, multiply and divide by x in order to join this value with this part. Let's see how I'm going to join this. H tending to 0, 1 over x remains undisturbed, and this part can be written as ln of 1 plus h over x to the power of x over h, because multiplication becomes power. So ultimately we are left out with the limit, and I can take the 1 over x outside, of ln of 1 plus h over x power x over h. If you look into it, this looks like ln of 1 plus y over 1 to the this looks like ln of 1 plus y power 1 over y. So let's graph ln of 1 plus x to the power of 1 over x and see what happens as x approaches 0. So this is the same as this limit. So let's graph this function. Let's graph only the 1 plus x power 1 over x and see what happens as x approaches 0. Let us see what happens to the point P as it starts moving on the line x, on the curve x plus 1 plus x power 1 over x. As it comes closer to x is equal to 0, observe the value of y. The y comes very close to 2.7 something. It is very close to 2.737271 something. Still in the negative part of the y-axis, 2.719 something. And when it crosses again, it is 2.71 something. So at the point x is equal to 0, you don't have the value of the function, but before and after the point it is 2.719, and from both the sides it approaches 2.719. Therefore, the limiting condition as x approaching 0 of 1 plus x power 1 over x should be equal to 2.713. So what we just saw in the graph was the limiting condition as x approaches 0 of this function is 2.71 something, which is actually equal to e. Therefore, this becomes 1 over x limit h tending to 0 of ln of, this is the function there, and I'm rewriting it for your convenience. I can take the ln out and write the limit for the function which is here. And we see that this limit is similar to this one, and this is equal to e. Therefore, we have 1 over x ln of e. And ln of e, since it is to the base e, it is equal to 1. Therefore, it is 1 over x times 1. So what we have found here is the derivative of the logarithmic function is nothing but e. Remember, this is only for the natural logarithm. It's not for any other base. Let's conclude whatever we have done so far. You have the functions in the first column and its derivatives in the second column. X power n is in x power n minus 1. The constant is 0. Sin x becomes cos x becomes negative sin x. E power x remains e power x. Ln of x is 1 over x. Very important thing to note here is sin x and cos x. In these two cases, we were using the limit as x approaching 0 of sin x over x is equal to 1. This limit was possible only if x is in radians. So, all trigonometric functions in calculus is done only when the angles are in radians.